Okay, so let us start the second part. Cosets and Lagrange theorem. Lagrange's theorem. So this is just a definition slide. Let me just explain it here for you. So let us say that I have a group, and I also have a subgroup of my group, and I have an element with from my group. Okay. I want to define for you what do I mean by the a left coset of H containing A. So this is the notation we use. This is called a left coset of this subgroup containing A. You will see why. Okay, and it is defined very simply by taking this A that you see here and multiply it by all elements from your subgroup and close the set. The set you generate in that way is called the A left coset, the left coset of H containing A. So this is the formal definition. Yes? So if I have a group and this is a group element, I give you a subgroup and then I ask you to form, for example, the left coset of that subgroup containing A. What do I mean by that? It means you pick that element that I gave you, multiply it from left by every element from H, it becomes a set. Whenever it is finished, you close that set. That set is called the left coset of H containing A. Now, can you tell me, is the name is a good name? Because I am saying that this is containing A. Do you agree this is a good name? Do you think that this set really contains A?
Probably not. Right?
If it is not a good name.
No.
Because I am saying that AH is called the left coset of H containing A. This is the definition that I have put there. So this should make sense. Otherwise, why should I say A is there? My question for you now is that, do you think if I construct this set, it always contains A or not? Yes?
Yes, because H has the identity element.
Yes, one of these elements in the H is the identity element. So if I multiply that A with my identity element, it becomes A itself. Yes? So you would say that A belongs to AH, since A can be written as A times E, and E belongs to H. So this name is a good name. It really contains A. But don't think that you generate a subgroup. Usually not. You always generate a subset. So if I ask you AH and G, this one is correct, or this one is correct, this one is guaranteed to be correct, but this might not be correct. Okay? There is some extra condition to make the left coset a subgroup as well. We will discuss about that, but I just want you to understand. And a similar idea is for right coset. Right coset means just multiply from the right. These are the definitions. And it doesn't matter if you prefer to work with left cosets from now on, or work with right cosets. I am used to working with left ones. The book, unfortunately, is used to work with the right ones. Okay, so that's a good opportunity. You will learn both. Okay, I will always go with the left coset. Whatever I will tell you is very similar. You just change it a little bit and see what happens. Any questions? So let me give you one example to understand how it works. So let us go to this example. Consider this subgroup of Z9. Write down all the left cosets of H. Yes? So I have given you Z9. By the way, when I don't give you the operation is addition modulo 9. Yes? So this means this is 0, 1, 2, 3, 4. Let me write all of them. This is Z9. And I have given you a subgroup. I have already given it to you. So you should, in principle, convince yourself this is indeed a subgroup. It's not hard. So H is a subgroup of Z9. And I am asking you find all left cosets of this subgroup. Okay? Yes.
Is that operation addition or what's the?
Oh, yes, operation is always addition if I don't say it for Z9. Addition modulo 9. Yes? Okay, so the first thing I will do, I will take this element. So in principle, I have to consider Z0H. I have to consider 1H for you. I have to consider 2H. And I have to consider continue this list until 8H. Yes? So I have to, because I want to find all left cosets, so I have to pick elements from here and find the coset for 0. And then I do it for 1, find the coset for 1, and etc. Containing 1, etc. Yes?
Do we have to do it for the identity? Don't we know that it results in the same?
No, because they are asking us find all of them, we will find them. Of course, the identity one will give you the same.
All right, yeah, we could, okay.
Yes.
Sorry.
But then one more thing that I want to mention, usually the operation that you see here is the operation of your group. So when we work with Z9, my operation is addition. So it is better not to use multiplication notation. So the cosets, instead of being denoted like this, they will be denoted by 0 plus H, and 1 plus H, and 2 plus H, up to 8 plus H. Yes? Okay, but let us do it together. So what is 0 plus H? It means take 0 and add it by which addition? Addition modulo 9 to all your elements in H. So I will add 0 to 0, it gives me 0. 0 to 3, it gives me 3 and 6, which is exactly as H itself. So let me do it later. So 1 plus H, what happens? So let us do it quickly. So it becomes 1, and this one, 4, and this one, 7. And then I go 2 plus H. What happens? It becomes 2, 5, and 8. Yes? Okay, but now if I go here, 3 plus H, what happens?
It's the same, right?
It becomes 3, 6, 9. But 9 is 0. So this becomes equal to this. Yes? So you see, 0 plus H is not written the same way as 3 plus H, but they are the same cosets. Yes, because after calculation, you see that this is happening. You understand that? For example, if I ask you what is 4 plus H, what is 4 plus H? So it becomes 4, 7, 10. But what is 10? 10 is 1. So it becomes 1. If I want to write it in order, it becomes exactly this one. Yes? And then if I go to the next one, do you agree this is also 5 plus H? Is that right? Or no? Is it?
Yes.
0, 1, 2, 3 is the same, 4 is the same. So 5, 8, and 11. So 5, yes, that's the same. 5 is this one, 8 is this one, 11 is 2 again. So that's correct. Okay? So then you continue for 6 plus H. So what happens? Again, it becomes the same. Yes? And then the other one, 8 plus 7 plus H, the same. And finally what? 8 plus H. So if I ask you how many notations you have, you will say I have 9 notations for the left cosets, but not all of them are distinct. So how many cosets I have at the end of the day? 3. These are the 3. But this one has 3 names. 0 plus H, 3 plus H, and 6 plus H, all of them are the same set. So they are not distinct cosets, even though they have different names. And that's extremely important for what is coming. So if I ask you how many cosets are there, I would say only 3 cosets I have. But how many names I could have a lot of names, by the way. You can see here I have 9 names. Is that clear? Okay, so what does it mean? Let us understand this. If I draw this consider this is your Z9. 0, 1, 2, up to 8 lives here. Okay? But 0, 3, and 6 together is this coset. Yes? 3 of them are here. And then 1, 4, and 7 are here. And then 2, 5, and 8 are here. Of course, the correct picture is that they are really of the same size because there are 3 elements here, 3 elements there, 3 elements there. But what do you see? You see a partition for your Z9. So it means that if you find all left cosets, the left coset somehow is very similar to equivalence classes. Okay? But the logic is different. Here we don't have any equivalence class yet. We don't have any equivalence relation. I didn't give you any equivalence relation. I gave you one set and one subgroup, and I asked you to find all left cosets. But it seems that the left cosets are somehow similar to equivalence classes. So that's a natural question. Is there any equivalence class, equivalence relation that I can define on a set whose equivalence classes become exactly these left cosets? And the answer to this is yes, I will see. But is the notion of a left coset clear? Okay. So let us go to the next one. So this is something I want you to do. Very similar idea. I want you to find all the left cosets. The same for this one as well. Yeah, this is a simple exercise, but you have to think a little bit yourself. Okay, remark 2. Note that the cosets are not necessarily subgroups. For example, which one of these cosets is indeed a subgroup? Can this one be a subgroup?
No.
No, because it doesn't have identity in it. Can this one be a subgroup?
No.
No. The only one that is a subgroup is the first one. Okay? And the reason is that this number that you see here as a representative is already in your set. Okay? So this is a simple theorem that I want you to prove it yourself later. So I would say that AH is a subgroup if and only if. Can you, based on this intuition, tell me what should I write there?
A equals identity.
If E is in AH, right?
If A is E.
If it is identity, that's correct. But because I want to write something equivalent. You see here, is 3 identity? No, but 3 plus H is still a subgroup. 6 is not the identity, but 6 plus H is still the identity, is a subgroup. So if you say it is identity, if it is identity, definitely this is true. But I want to write something equivalent to this all the time. Yes?
A belongs to H.
Yes. So this is a theorem that I want you to prove it yourself, please. It's a very simple one. Okay? So a left coset is not usually a subgroup. It is a subgroup if and only if this H contains this A from the beginning. If it contains, then that's correct. Understandable? Yes? Okay. So this is what I want you to prove. You will see this one as well. But this is a very important theorem. We want to talk about this one. There is a very nice theorem here, very simple to prove, but it is a little bit tricky because I was trying to do it myself. Then it took a while to discover it myself again because I didn't have it in my memory. What I want to prove in this theorem, I want to show that if you put all left cosets in one bag, and if you put all right cosets in another bag, there will be a one-to-one correspondence between these two bags. So let me explain it here for you. So here, G is a group. Yes. H is a subgroup. And then, yes. And then R is the set of consisting of all, so let me write it right cosets of right cosets of H. And let me write L to be the set of left cosets of H. The claim is that the cardinality of R is equal to the cardinality of L. So it means that if there are finitely many elements there, cardinality means the number of elements. The number of right cosets is always equal to the number of left cosets. Okay? So we want to prove this. So if I want to prove that the cardinality of two sets are the same, if the sets are finite, there is a very simple way. I can count them to see if they are the same. But if there are infinitely many of them, there is only one way to understand the cardinalities are the same, and that is establish a one-to-one correspondence between two sets. Is that right? So if I want to prove that the cardinality of L and R are the same, I should be able to define a function from one of them to the other one, which is a bijective. Okay, so 1-to-1 on 2. Okay, can you come up with an intuitive? Because whenever you want to establish a one-to-one correspondence, you should be clever enough to have an educated guess and then try to prove that what you guessed is indeed correct. Yes? Can you have a guess? It took me 30 minutes to find a guess because I picked the natural guess first. What is the natural guess? Can you tell me what is the natural guess? I want you to write a function that takes an element from L. What does it mean? It takes a left coset and gives you back a right coset. Do you agree? This is what I want. But I want to do it in a way that I can show later it is 1-to-1 and on 2. Okay? What is the first immediate guess comes to mind? Yes?
That you make AH equals HA, right?
HA.
Yeah.
That was exactly took half an hour for me. Okay, I was trying to force it to be right. Then I realized there is a counterexample, so I brought it as a remark. So do you think that this is a very natural thing? It means that yes? Yeah? This is the first thing comes to mind because this is a left coset, so it is chosen from L. And this is a right coset, which is coming from R. So apparently it makes sense to define the function in this form. Okay? But this is not correct. The reason is that this is not even a function. Okay? So let us keep it open for the time being. So this is not a meaningful function. Do you remember when I was talking about functions, do you remember I told you that you are not allowed to define the function in this form? Do you remember? This was an ill definition of a function. Why? Because if I ask you what is f of 1 over 2, because we know that 1 over 2 is equal to 2 over 4. They are the same. But if I ask you what is f of 1 over 2, you would say 1 plus 2, which is 3. And if I ask you what is f of 2 over 4, you will tell me 6. So this means that even though the numbers are the same, they are not being mapped into the same. So that's not even a function. So that's not even well defined. The problem with this definition, which I didn't care myself first, and I was in trouble for 30 minutes, is because this is not a function at all. What does it mean? It means it is possible, it is possible that you have this scenario. This happens, you see, this and that one are written differently, but they are the same. But they are not mapped to the same. And this counterexample, I have brought this for you. So you cannot conclude from here that the other way around is true. This was, I was not expecting that, okay? So that's why I actually spent a lot of time. So if these two are the same, there is no guarantee that the other way around is the same. If you want, if you are in a hurry, I can show you the counterexample I finally came up with. Okay, so that's the counterexample. So if you do this, it is not very hard to show that if H is this subgroup from S3, then this one multiplying this permutation by h, the left coset of h containing this permutation, is equal to the left coset of h containing this permutation, but you can easily show that the other way around is not correct. I really want you to go and think about it yourself. It's a very simple calculation, extremely simple calculation. Okay? So this means that this is a very natural definition, but the point is that this is not even a function because of that counterexample that you can check at home. Is that clear? Okay, so if that is not correct, unfortunately, the easiest one is not correct. So reluctantly, we have to cross it over. And now we have to come up with another one. Do you have another one in your head? So I want to define again something from the left cosets to right cosets, 1 to 1 and on 2. I will definitely keep this one the same, but I want to change the right-hand side. The right-hand side there didn't work. What is another one comes to mind? Then it is not that easy, but you have to have a little experience. But it should be something related only to A. Okay? So if H, so you know that H should come on the left. It was not that hard, by the way. And something should come here. But can I say B? B is stupid, you know? Why? Because what is B then? I am supposed to give you something when you give me AH. I have to give you something in return. So what is B? I don't know. So HA was a very natural one, which unfortunately didn't work. So what is another guess then? So you see, if you think in that way, it comes to mind. So it should be A inverse, and it works. Okay? So at least you have your educated guess. So this function is a one-to-one correspondence between R and L. Is that right? Proving this is not hard, but be careful. Here you have to show that this is a well-defined function, because you realize that cosets can be the same, but they might have different names. So if you want to prove that this is a one-to-one correspondence, in normal situations, we start with proving injectivity and proving surjectivity. But if you define it in this way, this might have different symbols symbolizing it. So there is one more step you have to do before every one of those. You have to show that this is indeed a well-defined function. Is that clear? So let me repeat. If I give you a function and I ask you to prove it is injective, and it is bijective, you start with proving injectivity and then proving surjectivity, and you are done. Okay? But if I define a function in this form, because you learn that there might be different names for the same thing, first of all, I have to show that this is indeed a function. Do you agree with me or not? You want to show it's a function. So how should I show that this is a function? So number one, f is well defined. Well defined means you are respecting the grammar. It means that is it coming from L? Yes. Is the answer coming in R? Yes. So you are respecting those things, but you should also define that you should also prove that this is a well-defined function. What does it mean? It means that if you give me AH which is equal to BH, I have to confirm that f of AH is equal to f of BH. So if you are defining a function in this form, this is very comparable to what I am saying here. You see, this 1/2 and 2/4 are different names for the same number. And you see that even though they are the same, the results are not the same. So this function is ill-defined. Okay? So I want to make sure that this function is not ill-defined. It means that if AH is equal to BH, f acting on AH will also be equal to f acting on BH. Otherwise, I have that trouble there. Okay, how can I prove this? So instead of this one, I write the result. So f of AH is H inverse. HA inverse equals to HB inverse. So that is my goal. If AH is equal to BH, I want to prove that this one is equal to this one. Okay, so how should I do this? This is your assumption. This is what you want to prove. How should I prove this in general?
If you expand the functions, you can do it by cancellation.
What did you say?
You can do it by cancellation by expanding the function.
No, cancellation is only for elements, not from sets. Yes. So, for example, I cannot cancel h's.
Yeah, yeah.
If I have a little h, b little h, I can cancel h's. Because cancellation works in a group. Yes? I am not allowed to cancel subgroups. If you are, you have to prove it already, okay? Which is not the case. And this shows it is not the case because you see 3h is this, if I cancel h, I get 3 is equal to 6. That's not correct. Okay, but now
Divide the sets as
Yes.
elements h1 to hn, right? So
pardon?
you just showed elements. So I
Yes,
just
exactly. This is equality between two sets. So don't forget about this.
Subset.
Whenever you want to prove two sets are equal, you have to show this one is a subset of that one and the other way around. There is no other way. So this you have to repeat until you learn it. This equality you want to show is equality between two sets, and there is one technique to prove that two sets are equal. Okay? So I would say that let AH be equal to BH. We prove that HA inverse is equal to HB inverse by proving that, okay, complete it for me, by proving that what? What? HA inverse is subset of HB inverse and HB inverse is a subset of HA inverse. Is that right? This is what we want to show. Okay, so let me again, because they are very similar, let me do one of them and then you can do the other one yourself. So proof 1. Okay, so I would say let x belongs to HA inverse. We show that what happens? Yes? But this is a little bit tricky. Hopefully I can reproduce it again on top of my head. So how should I do? How should I continue? So you see, I have this assumption. I know this is true. I want to show this one is true. To prove this one is true, I have to show both of them are true. I started from this one, picked one element there. I want to show it is on the right side. This is the strategy. But tell me, how should I start? I start from here. X belongs to HA inverse. What do I conclude from here?
there is an element in H.
Yes, there exists an element H in H such that X.
XA equal to H.
Oh, write it immediately. So you are calculating something in your head. X is equal to H A inverse. That's the meaning, yes? That's the meaning of being a right coset. It's a right coset including A inverse. So when I say X belongs to this, it means that X can be written as a product of H with A inverse for some particular H. But the point is that my goal is to show, so I go to a scratch paper to see how should I go. My goal is to show that this X belongs to this one. If I want to do this, I have to go to a scratch paper and ask my question. My question is that I want to show that X belongs to the inverse. This is my goal, okay? And then I ask myself, when do I succeed to show this? I succeed to show this if there exists an H prime, not necessarily the same H, such that, can you help me? Such that X is equal to what? I need to convince myself that there exists an H prime in H such that X can be written as what?
H prime.
H prime the inverse. The reason I am asking you to go to a scratch paper because might be guessing this H prime is not easy. I have to calculate and claim something and prove it. Is that right? So, okay, can you now guess what is this H prime? Because the answer is supposed to be X and I already know X is of this form. So this means that H prime B inverse at the end of the day should be equal to HA inverse. Okay? But do you remember I was looking for this H prime? Okay, so can you find this H prime now? Is that right? I multiplied from right by B. So this means that I was able to find this H prime. Okay. So if I have this H prime, I am done. Yes. Okay. Now everything in a scratch paper. So I come back here. So what I will do, I want to make sure that this can be written as that H prime by this. So I will continue in which way? Can you help me? Okay, so let me write like this. So I would say that x is equal to h a inverse, but this can be written as h a inverse b inverse. Do you agree?
Yes.
Yes. You see this, I couldn't guess this one is useful unless I did this calculation. But if you are smart enough, you could come up with this combination, because this combination is nothing. You see, instead of this one, I wrote b and b inverse. Yes? So x is equal to this one. Instead of this one, I have written it here. But my question is that, do you believe that this belongs to H or not? Because if this belongs to H, I am done. This is an element from H multiplied by B inverse. Any element from H multiplied by B inverse is an element from the right coset of B inverse. Understandable? So you see, if you are confused, momentarily forget about this. I started from here. My goal is to show that X belongs to HB inverse. By definition, everyone agrees that this can be written. Okay? But let us imagine that you are genius. Suddenly you understand that you bring B and B inverse. By the way, you don't need to be genius because you want to show that X belongs to this one. So it means that you need B inverse on the right side somehow. The expression that you have has A inverse on the right, but you want to have B inverse on the right. Okay? What can I do? I write B inverse on the right, but I have to compensate for my change. So I put another B there so that they cancel out. On the one hand, I am doing nothing. On the other hand, I have my B inverse on the right side that I need. This is another way of thinking. Is that right? But the only problem left is that, is this element in H?
Yes.
I know little h is in H, but I don't know anything about A inverse and B. But my claim is that, I will come to you. My claim is that A inverse B is always in H because of my assumption. Okay, because you see that I haven't used my assumption yet. I have only started from what I want to show, and I was able to go up to here. Okay, that my goal is to show this. If AH is equal to BH, my goal is to show that A inverse B belongs to H. If I can confirm that, then I am done. Because this part belongs to H already belongs to H, and H is the subgroup. So this means that when I multiply them, it becomes in H. Is that right? So this one, if you can prove it, then everything is done. Clear? Okay, but this I want to leave an exercise, as an exercise, okay? Do it. Okay, there's no time, so that's why I want to rush a little bit. Is the logic clear? Okay, so you have to go home and see why this assumption gives rise to this. By the way, in algebra, it is good to have this in your memory as well. Okay? And if I can prove this one, then I am done, because this will be in H, this is in H, so this becomes something in H. Something in H multiplied by B inverse, it is definitely in the right coset of B inverse, of the H. Okay. Any questions? Okay, so please do that when you go home. One more thing, so, by the way, this is just well-definedness. The other ones are very simple, they are not hard. What else I have to prove? Now that I am sure that my function is well-defined, I have to show it is one-to-one, I have to show it is surjective. Okay, please do those as well. Okay, they are very similar. But if you do them, it means that there is a one-to-one correspondence between L and R, so it means the cardinality of this and the cardinality of this are the same. And there is a name for this cardinality. That is called the index of the subset. So the cardinality, so let me write it here. The cardinality of R is equal to the cardinality of L, and the name of this common number is called the index of H, the subgroup in G. And there is a symbol for it. It is denoted by this symbol. I don't know why the book has chosen this symbol, but this is the standard one. We put the square brackets. The book has used this one. This is called the index. Okay? So it means that if I ask you what is, for example, can you tell me what is the index of H here? This one Z9, and this is H. If I ask you what is the index of this subgroup, you should count the number of left cosets, which is the same as the number of right cosets. That number is called the index of your subgroup. But because we have already done that here, so can you tell me what is the index here?
3.
The index is 3, because how many different cosets I have? 3. And the Lagrange theorem tells you a formula to calculate it. And the formula is simple. The number of these elements divided by the number of these elements. It's 3. So that is the Lagrange theorem. We will come to it now. Okay? So this is very important to understand. Of course, Lagrange theorem is only for finite sets. Okay? But cardinality makes sense even if your set is not finite. For example, the cardinality of the set of natural numbers is not a finite number. The cardinality of integers is not a finite number. But have you seen that? The cardinalities are the same. The number of elements within the set n and the number of elements within the set of integers, including the negative ones and 0, the numbers are the same. Because we can put them into one-to-one correspondence. And this is not hard. Think about it. Find your bijective function from n to z. And very simple, it's not hard at all. But in the beginning, it's very confusing. How is that possible? The number of these infinities are the same, because one of them includes all negative numbers as well. Okay? Okay, now, this one you can do. This one, let us do this one. And you see that this is exactly, this expression is exactly what happened here as well. Okay, so let us do this theorem. This is a very, very simple theorem. You already, hopefully you understand that there is some relation between cosets and equivalence classes. You remember that was my question for you. The problem is that the way I stated the problem, you didn't even see an equivalence relation there. You just calculated the left cosets and you realize that the left cosets are partitioning your original group into different groups, partitioning into different subsets. But you had this picture in mind before the break. It was very similar to the equivalence classes. So there was a natural question, is there any equivalence relation that I can put on the group so that the equivalence classes become equal to left cosets or right cosets? And that is your relation. It is good to remember that relation. Okay? So we want to prove this. So let us do this together. So you see, if you give me a group and a subgroup, I can always construct an equivalence relation on my group using the subgroup. Okay? How? Exactly according to the theorem I have written there for you. You say that for all A and B in G, I would say that A is in relation with B, is related to B, if and only if A inverse B belongs to my subgroup. You give me a group and a subgroup. Using these two ingredients, I can immediately construct an equivalence relation for you on the group without even knowing what G and what H are. Okay? So let us prove it. I have to prove a reflexivity. So how should I prove it? I should prove that for all A in G, A is related to A. Is this true? Yes, because A related to A means A inverse A belongs to H, means E belongs to H, and this is true because H is a subgroup. Yes? The next one, symmetry. I have to convince you that for every pair in G, if A is related to B and B is then B is related to A. How do you think we can prove it? This is what we want to show. So I say that A related to B according to the problem means A inverse B belongs to H. Do you agree that if an element is in a subgroup, its inverse is also in the same subgroup? Yes? But then what does this mean? According to socks and shoes, I can write it as B inverse A belongs to H. And do you see what happens? This is the same expression except that A and B are swapped. So this means that B is related to A. And finally, for all A, B, and C in G, if A is related to B and B is related to C, we want to show that A is related to C. So how can I prove this one? I start from here. This means A inverse B is in H. This means what? B inverse C is in H. What do you think I will do? In what I want to show, I want to get rid of B. So I have to do something legal that B is cancelled. So what should I do? I should multiply them, yes? So this one is in H, this one is also in H, because H is a subgroup and subgroup is closed under binary operation. So it is guaranteed that A inverse B multiplied by B inverse C belongs to H. But because of associativity, B and B inverse are cancelled. What do I get? I get A inverse C is in H. And then what happens? This means that A is related to C. So you see, if you just give me a group and a subgroup, even without knowing what that group and what that subgroup are, I can immediately construct an equivalence relation of it. Okay? And now what I want, this equivalence relation is the one that we were expecting. Okay? Now it shouldn't be hard for you to show that the equivalence class of A is exactly the left coset containing A. Yes? So this is something you should prove yourself. Write the definition of this one and it actually becomes exactly equal to this expression. So this means that this equivalence, so it means that the properties of these are the same properties as equivalence classes. For example, can this be empty? No, because this one is an equivalence class. Equivalence classes cannot be empty. So this cannot happen. For example, do you remember this was true? This was true. So now what can I say? I can say that A always belongs to AH. But one thing that is very important, do you think if I have two left cosets, what are the relative situation between two left cosets? Two left cosets, this one can be viewed as this, and this one can be viewed as this. Do you remember what was the situation? They are either equal or they don't have anything in common. So the same thing happens for these. So I can say that AH is either equal to BH, or, can you complete it for me? Or AH intersect BH is empty. Okay? Exactly. So you don't need to prove everything for the left cosets, because what you did, you proved that this is an equivalence relation, and you should go and prove that equivalence classes are left cosets, and then whatever property equivalence classes had, left cosets will inherit them. Is that right? So you don't need to prove it from scratch all the time again. Okay. But I think it's better not to go much forward. The idea of Lagrange theorem is this. Let me at least mention it. Might be we'll complete it after the yes. Let me see what more we have here. Yeah, this I have written all those lists as a remark. So this is the Lagrange theorem. At least we can phrase it here. It's a very simple, elegant theorem. If G is a finite group, and H is any subgroup of G, then the order of the subgroup divides the order of the group. Okay? I think you can come up with the proof yourself, more or less now. So the idea is this. If you give me a finite group, do you think that I can write this finite group as the union of left cosets? I just want you to tell me, but then formal proof will be left later. So do you think that if I give you a finite group, do you think that this finite group can be written as the union of left cosets of this subgroup? For example, A1, union A2, union, etc. For example, let us say I have R of them. Yes? Do you agree that this can happen? Why? Because these equivalence classes form a partition, and one of the properties of the partition is that when you union them, it will make your set. It gives your set back. Now, equivalence classes are left cosets, so the same thing happens. If I union my left cosets, the union becomes my original set. Okay? But I also know that there is no intersection between different sectors. So can you tell me what is the number of elements here? The number of elements here, because that is a non-overlapping union. If I want to count the number of elements here, I count the number of elements in each one of them and add them up. Is that right? But the point is that there is one thing that is left for you as an exercise. We can do it later. The number of elements in all left cosets are the same, and it is equal to the number of elements of the set H itself. And that's done. Because if I know that, so if I ask you what is the number of elements here, this becomes the number of elements here plus the number of elements in the last one. But if I can show you that these numbers are all the same, you can write it as R times one of them. And if I can show you that the number of elements here is equal to the number of elements in H, then we are done. So it means the number of elements in G is a number multiplied by OH. So it means OH divides OR. So that's the proof. So the only thing that you have to go home and prove is this. Cardinality of AH for any A is equal to the cardinality of H. So if we, actually this is the proof, exact proof. The only thing we didn't show is this one. And that is a very clear one. Can you guess what is the one-to-one establishment here? Because if you want to prove cardinalities are the same, you should have what? You should have a bijective function. F of h, tell me, what's the answer?
It's a little h, right?
A little h. Very natural. You can prove it immediately that this is a bijection. If it is a bijection, the number of elements here and there, they're same for any a. So everything is now formalized. So but actually we were able to prove it. That's the proof. Yes.
Can H be any kind of sub?
Any kind of subgroup, but the original group should be finite. Okay? So, okay, I know that you are willing to immediately go, but let us just ask you this question. You have a group of finite group of prime order. What are the subgroups of that? For example, I give you a group, you don't know anything about the group, but I tell you the order of my group is 31. And I want you to find all subgroups of this. What is that?
Only identity
One more.
and itself.
And itself. Yes? Because if H is a subgroup, according to Lagrange theorem, order of subgroups should divide 31. But 31 is prime. So there are only two options. 1 and 31. 1 is the one only containing identity, and 31 is the whole set. Okay? But be careful. If I give it 32, there are a lot of options. But there is no guarantee you have a subset of. For example, 4 divides 32, but there is no guarantee that you always have a subgroup of order 4. Unless you know something. What is that something? We had it before. The group is cyclic. If the group is cyclic of order 32, for every divisor you have exactly one subgroup. But this is no longer true in general. So if I give you G of order 32, nothing more, even though 4, 8, 16 are divisors of 32, but there is no guarantee there are subgroups of those orders, unless the group is cyclic. Yes? So the converse of Lagrange theorem is not in general true. Okay? Yeah. Thank you very much and have a nice break. Yeah, thank you.